As we continue to talk about energy methods, today we introduce the principle of the conservation of energy. Before we do that, we have to make a definition here. Conservative force. Conservative force is one where the work done depends only on the starting and finishing positions. Now, we already showed that for a weight, the work done doesn't depend on the path at all, but only the total height that's dropped to do positive work, or where the weight's lifted to do negative work. And a similar example is the force in a spring. The work done only depends on the delta, the extension or the contraction at the beginning and at the end. If it's stretched and compressed beyond, during the time from 1 to 2, that doesn't affect the total amount of work done. An example of a non-conservative force would be friction. We also talk about potential energy now when we talk about the conservation of energy. Potential energy is given by the symbol V, and for a weight, the potential energy is simply the weight times the distance above some datum. So we say that potential energy is W times H. For a spring, the potential or stored energy is 1/2 K delta squared. And so it doesn't matter if the spring is stretched or compressed because of the fact that the delta gets squared in this equation. So now that we have that definition in mind, we can say that if we don't have any non-conservative forces, that only conservative forces are present, then the mechanical energy, which consists of the kinetic and the potential energy, doesn't change from one state to the other. So at our initial position, we'll say we have kinetic plus potential. Then at the final position, that total of potential and kinetic energy is going to be the same. So here's an example problem. So a lot of the problems we work with conservation of energy include weights and springs. And so in this case, if we drop this weight onto a spring, and the question is, what's the maximum compression of the spring? So there's our condition 1, is right before we drop it, and condition 2 is when it comes to a stop at the maximum compression of the spring, the compression of the spring given by delta. And for this, we've defined the datum for the potential energy of the weight as being the top of the unstretched spring's platform. So the initial kinetic energy is 0 because we're dropping it from 0 velocity. The initial potential energy is the weight times the height h, the distance above the datum. The final kinetic energy is 0. It's coming to a stop at the maximum compression. And now for the final potential energy, there's actually two terms. Remember that we have the 1/2 K delta squared, the energy that's now stored in the spring, but also the weight is now below the datum, and so we have the minus W delta as a term there. So now we set the total energy at 1 equal to the total energy at 2. And rearranging the terms a little bit, you can see that we have a quadratic equation to solve for delta. Now, what if instead of selecting the top of the unstretched spring as the datum, what if we selected the final position as the datum instead? Well, again, our kinetic energy would start at 1 again, but now the potential energy at the beginning, because now we're h plus delta above the datum we've chosen, would be W times the quantity h plus delta. The final kinetic energy is 0, and because the weight is now at the datum, the only term for the final potential energy is 1/2 K delta squared, the energy again stored in the spring. So applying our equation again to equate the energy and rearranging the terms, you'll see that we do have exactly the same quadratic equation. So what we see out of this is it doesn't matter where we choose the datum as long as we're consistent from 1 to 2. Now several problems will involve multiple springs, and so just a review of how to handle springs in series and parallel. If we look at springs in parallel first, which means that there's just two of them side by side, two or more side by side like this, we can replace that with an equivalent spring that has the same load deflection characteristics. And to do that, we simply add together the spring constants K1 and K2 to get the spring constant of our equivalent spring. When springs are in series, that is attached end to end, like in the top picture here, K1 and K2, again we can replace that with a single spring with a spring constant K equivalent. And in this case, we have to add the reciprocals of the spring constants, and so 1 over K equivalent is 1 over K1 plus 1 over K2. So in this case, you'll find that the equivalent spring has a spring constant that's lower than either of the constituent springs because both of them are being stretched. So in the next class, we'll finish up with the classes on energy methods, and so we'll look at problems involving work and energy, power and efficiency, and conservation of energy.